So Reinaldo is Director on Wireless Communication Research Department of Bell Laboratories. He has been engaged in MIMO and space-time system encoding and achieving high capacity using transmit and receiving path of antenna arrays, and involved in next-generation air interface technique and architecture. He has published a lot of papers and has been heavily cited on Google Scholar for his work. So he will talk about the new advance and technology in physical wireless layer, and give him the talk. Thanks, Reinaldo.
Okay, good morning. It's a pleasure to be here. And in the interest of provoking dialogue and a lively session, considering that we're coming to an end and perhaps getting tired, and also we're starting to hear certain themes that are consensus or perhaps at least revisited. No point in taking too long to go over them. So I'm going to try and and touch upon actually a broad spectrum, 5 different topics, but I won't bother you with a detailed math, but rather to try and generate some discussion. It's pretty obvious. You heard now yesterday and today, very well articulated by Telefonica that has a lot of data. We are, in my opinion, at a structural transition in the industry. We can no longer ignore what I've been calling now for something like 2 years, the too much data paradox. It was fun to believe that you can have all the data you can consume and have high definition in every terminal everywhere. If you look at the AMT 2000 goals, that was all great until we figured that somebody has to pay for it. And there is no guarantee or laws of physics that says that it has to be affordable and everywhere and everything else. So what exactly is going to happen? A lot of very good questions. Until that time where the industry settles itself, every possible way of squeezing more throughput at a lower cost is going to be incredibly important. If you follow the cost reduction trends, it's not very encouraging because you see annual aggregate compound rates of maybe 10, 20% if you're lucky. We're talking a factor of 30, 15 times, 10 times. So cost reduction by itself is not going to do it. But when we look at techniques, whether it's MIMO, whether it's picocells, we need to keep thinking about which ones are going to be the cost-effective ones. So that's a little novel for us working on the fundamentals of physical layers, but that's going to be a theme through the discussion. Now, relays is a very interesting topic because, of course, academia has been looking at relays for a long, long time and probably not coming up with much wisdom that can be applicable to industry. It generates a lot of math problems and generates a lot of PhD theses, but not a lot of really good industrial insight. So we've taken here an alternative look, which is, while trying to push the envelope on the COM theory, try to bring it to a level where we can begin to perhaps illuminate the discussion of whether relays are ever going to play a role in real-world networks. And so just some quick definitions. We have a base station, a macro, and we're adding a little black station there, a relay station, and typically you have 2 phases. One is base to relay, and you can think of it as time slots or could be frequencies, but time slots is a good paradigm. And then in the second time slot, the relay communicates to the user. Right here, you see a whole number of questions arise because you cannot say that this situation must be imposed all the time. What if the user is very close to the base? Then there's no point in using the relay. You may actually end up behind rather than ahead. So while in academia, it's typically assume you go source a relay destination, and they spend a lot of time with their collaboration or not collaboration and a variety of schemes. Well, if you put a real propagation and look at the statistics, then you need to first figure out what actually is, depending on the particular instantiation of location of the users and propagation channels, what base is talking to what users directly because they're close, and what cases you're actually going to rely on the relay to help you. But the beauty of the relay is that it does not require backhaul. So let me a little bit connect with the previous talk. 100% agree. Introducing a lot of small cells, and cell splitting, of course, is extremely powerful because in the networks, it's easy to get yourself to a situation where you're interference limited rather than noise limited when you're driving up for capacity. And then it becomes obvious at the interference limited setting that everything is just a matter of ratios of distances. And so when you're talking about ratios, it doesn't matter if the units are kilometers, tens of kilometers, or meters. So you can be scale independent, and every time you reduce the scale, the capacity per unit area goes through the roof. So cell splitting is fantastic. But remember the cost argument. You need to deliver backhaul capacity to every one of those picocells. So relays are very attractive because obviously I am talking about in-band co-channel backhaul. So the message to the user is coming to the relay from within your own resources. So the idea here is that the relay ought to be something, small, inexpensive. You stick it to the wall, and perhaps even gets power from solar, and you forget about it. That kind of a very inexpensive deployment model may allow us to massify the introduction of relays. So that's now, academia loves the story about collaboration. What's collaboration in relays? Well, simply the fact that while the base station is communicating with the relay, the destination may be overhearing that communication, and it could be storing up that information, as the COM theory terminology would be, you could be accumulating mutual information. It just simply says that that is the same message you're eventually going to try and decode, so why not take advantage of whatever information you can collect during that period? So that would be the collaborative type. Non-collaborative is just 2 time slots, and transmissions are completely ignored if your time slot is not the one in your listening. There's a whole variety of other algorithms, but in the interest of time, I'm not going to spend too much time here. So I've discussed already the 2 phases. So a lot of action in academia has been, one relay in the middle. And of course, we're a little shy to start putting a lot of these relays in the network, so a lot of time has been spent in seeing what can you do if in green here you put just 1 relay some way halfway down the sector center. Now, if you look at that network view, COM theory very quickly abandons you. It's not tractable, you cannot do it analytically, so you need to resort to simulations. Even when you come to simulation, if you wanted to still have a very fundamental view and say, give me the highest possible cost to optimum throughput you can achieve in this network, because this is all idealized. So then you're going to have to, add penalties due to implementation. If the gains are not large, maybe we just stop right here. So let's first try to go for maximal possible gains. Well, maximal possible gains would require for you to decide on a network-wide basis, or at least within a cluster where interference is still relevant, who is talking to whom, in what slot. Base station to relay, base station to use it directly if you're close, or then, of course, relay to destination. Well, this is a massive dynamic optimization that nobody knows how to solve. So we took a simpler situation where we took the hexagon in the middle, where you see 3 base stations pointing to the 3-sector vertex, and we considered that a key unit. And we solved that optimization within that unit. And then, of course, it tessellates, meaning shifted versions of the same cover all space without overlap and without gaps. So they can all be doing the same optimization while ignoring what the other ones are doing. So this is suboptimal, but at least it's doable. You can simulate it. And of course, we account for the out-of-cell interference, but not try to do the global optimization because it's just not tractable. And lo and behold, we found what in 3GPP and others have found, the gains are pretty abysmal, 20%. Now, you can do tremendous improvement at the edge, because of course the relays are getting you close to the edge, so you can improve edge performance. But this is not very encouraging. But we decided not to give up, and we said, well, if these things are really going to be so cheap and inexpensive, maybe the gain is in massifying a little bit the introduction of resources. So here we go to 2 relays per sector, halfway down. But now you have many more radios, and also we put antennas, more antennas in the relays. So we have 2 relays per sector, 3 antennas on each relay. So now you have 6 degrees of freedom. You can serve up to 6 users simultaneously. Spatial reuse, degrees of freedom, whatever. So now we are building up at least our potential. And we're going to see, going to save the punchline a little bit towards the end. The details of the technologies I'm going to skip in the interest of time. Another one we can do, and while doing the simulations, you very quickly start realizing that the intuitive halfway along the sector is actually the wrong place to put them. Becomes also very critical, but very hard to do in a fully optimized manner if you add the question, where do you place the relays? Well, it turns out that find where the interference is worst and plop the relay right there, because those are the user locations that need the most help. And you can help them the most by putting a relay at the shortest possible distance. So this motivated a third option where we put all relays together, collocated, if you will, as a Huber relay that now has 6 antennas and is located at the precise vertex of the 3 sectors. Idealized geometry, but it gives you perhaps an intuition of what may happen in the real world. And so here is the table of results. And just idealize on but now you see that the last 2 options where I'm increasing the amount of radius, I'm increasing to 6 the combination of, whether it's 2 relays with 3 antennas or 1 relay with 6 antennas. Now we see, 200% plus improvement in average throughput. And believe me, average throughput is the one metric that matters, because you divide average throughput by average rate per user, and what you get is number of users paying $40, $50 a month. That's revenue. So far, nobody's been able to monetize peak rate improvements. That's QoS, that's mushy, we can do it, but nobody pays for it. So what you want is average rate without damaging the edge rate. Now, if on top of that, you actually also improve the edge rate, then of course you have a win-win scenario. But actually, the best metrics, and we're not quite there yet, would be going for the full throughput improvement at the same edge rate performance. That would be an apples-to-apples comparison. So anyway, how about small cell and heterogeneous cells? Well, absolutely, we love them. But of course, here we're taking the extra cost of putting a backhaul to each one of them. But we still wanted to understand those scenarios. So we've done detailed analysis using 3D ray tracing, very advanced understanding of the electromagnetics, this type of scenario where you have dense urban with a lot of apartments, and we assume that you have an access point in every apartment where you would have a lot of interference. Now, what you learn very quickly, very much in the same spirit that my colleague from Qualcomm was saying, it becomes critically important to manage your interference. Now, here is the market's business privacy issue. If you have a unit, whether it's a femto provided by the service provider or whatever, in your own residence, are you going to allow other unknown third parties to be served through your unit and their traffic to go through your perhaps backhaul connection to the network? That's a key issue. If you don't, then because of privacy, whatever reasons, or because you don't want to subsidize somebody else through your own backhaul, then you're going to have users that may be right outside your window where the power levels are such that the radio performance gets really degraded. So when you don't let the outside users, it's called closed user group, and has that kind of problem. The other option is open user group, as you see there. So we've done a lot of simulations, and in this, what we learn also is that as you start talking about femto and picos and small environments, classical 3GPP models that are based on statistics go out the window very quickly. And you either have to do measurements, which is very expensive, or you now need to go to site-specific ray tracing, where you have to have the actual morphology, the database with the buildings, building heights, whether it's very different, whether it's an open plaza, or whether it's the dense urban with skyscrapers and your antennas are below the clutter. So we've done that, and you see here the type of issues. The downlink interference from the macro that we thought it was going to be a problem, it's typically not a problem, but the femto to femto interference can be quite a problem. Now, interference avoidance and MIMO, of course, are key ingredients, and as you see from the previous talk, interference avoidance simply through shifting bias, it very quickly it becomes very clear that you have to do that. If you keep the parameters as per original macro design rules, it turns out that if you put a few pico of the order of less than 10, they attract so little traffic that they make no difference. You need to start adding hundreds of picos to the point that you could almost just turn the macro off for the gains to really settle in. But you can achieve more of the gains with fewer picos with the bias shifting. How much more time do I have? Okay, good. I'll wrap it up. So we're also finding, as you heard, 50% of traffic is already, 70% of traffic is already being offloaded. So to us, it's becoming pretty obvious that the notion that cell phones are car phones or even outdoors is the main activity is perhaps shifting. If you're a really heavy bandwidth user, perhaps you're in front of a significant screen, and perhaps you are inside a dwelling. So maybe we need to start giving more emphasis to carrier grade enterprise solutions. I mean, how embarrassing for all of us collectively in the industry is to have Steve Jobs in the Metro Zone, whatever it's called, center in California, and his own system totally collapses because everybody's on .11 and it's just brain dead. I mean, well, of course we know you could fix it, but why? How come it's not yet fixed? Well, that's the business case scenario. The ecosystem in that environment is sort of consumer electronic driven. You sell one unit at a time and hope for the best. Maybe it's time that we have carrier-grade enterprise solutions that are targeted for indoors, but they have the robust interference management, power control that would allow to, interference is not the problem. We know to survive 0 dB interference, negative interference. We have modulation and coding rates that will give you quite generous bit rates with sufficient spectrum, even at heavy interference. But of course, you have to build that into your system, which Wi-Fi today doesn't have. So this is why we're looking at indoors. Again, very realistic ray tracing. And we see dramatic gains can be had. As you see from the other techniques, getting a tripling, getting a quadrupling of capacity is getting really, really hard. But particularly indoors, use of multiple antennas. Again, in the multi-user scenario where the terminal perhaps is still very simple, single antenna, but you have an access point that now is richer with, say, 4, 6, 8 antennas, and it could perhaps support 4, 6 sessions simultaneously, depending on geometric location. With the, of course, tricks that you need of the trade here, because it's not line of sight, so you may need full channel state information at the transmitter to do the multi-user MIMO tricks, in which case probably you better be off in a TDD network than FDD. So very interesting implications for physical layer, for comp theory. As the squeeze is coming in to get these factors in an economic fashion, all of a sudden we're going to perhaps be facing technical choices like, even if you have FDD spectrum, wouldn't you be better off, at least on enterprise solutions, to exploit it as 2 TDD systems and take full advantage of a lot of antennas in the fixed points, but very inexpensive terminals? Interesting questions. And you can see here, again, the table for indoors now, how as you go from 500-meter intercell, the macro as a reference, if you go to 150 meters, you go to 10 meters, then what I said about cell splitting comes really, really strong, and you have huge factors gains that you've been hearing all along. There is no denying that, with that close to distance to the 4th power, if you cut your distances in half, you get 16 factor right there. So reducing cell size, we're not going to be able to ignore that, without leaving in the table huge potential gains. So that's all for small cells. There is, I want to do a quick pass through backhaul, because if you want to do picocells, obviously backhaul is a huge issue. And when you hear people, perhaps like Misha Dor, saying physical layer is dead, well, there are many aspects of physical layer. This is one aspect that that is very critical. What do you do over your run to do all this backhaul? And with the MIMO, particularly the network MIMO flavor, you need gigabits perhaps of backhaul. Well, one observation is that the signals that you're going to try and transport in quasi-analog fashion, digitized I and Q, well, first of all, it's obvious to you that you have guard bands that were needed over the air, but they're not needed over the cable. So we can immediately go do some filtering. And so here is the filtered version. And then we can also do, if we're in this much more controlled, digitized version of the analog world, we can do block scaling, essentially fast AGC. So we can look at the data and see what your maximum values are, and we can quickly scale. We add to this nonlinear quantization, which may be familiar to you, and we've shown that we can do a factor of 3, maybe more, 3.5, depending on how much you want to, the filtering. Maybe introduce a little distortion, but you can control it. It was before 7.7, going up to only 8% distortion in the electric. You can triple 3.5 times reduction on your backhaul needs. That's a huge number. It takes you, a gigabit per second now becomes only a 300 megabits per second link to enable perhaps these advanced MIMO features. So I think in the interest of time, perhaps I should, I'm running out of time? Okay, and so very, very quickly, this is all good, but as we deploy more and more, the issue of power consumption is becoming very urgent. We're also conscientious citizens, and we should do our part to look at the green issues. So one interesting, which is sort of like totally contradictory to our normal way of operating, but being in research, we get the liberty to at least explore the fundamentals and explore new directions that may not be obvious. So if you at least pose the question, suppose like perhaps through the dynamic spectrum access like Milena was talking about, suppose you were free to use large amount of spectrums. Could you trade that off for lower power? It's very intuitive. The COMP theory tells you you should, because if you have plenty of spectrum, you could operate a very low spectral efficiency through advanced coding, and therefore you have huge advantage over noise. Well, this curve is telling you exactly that trade-off. Oh, sorry. So you can see that you have a power efficiency on the left and bandwidth. And as you use more and more bandwidth, your power required is quickly dropping. So if you stay with the qualitative shape of the curves, you see that you can do perhaps 1/50th of the transmit RF power if you're prepared to burn 10 times the spectrum. Now, Telefonica, please don't get all upset about using 10 times the spectrum. It's probably not something that you want to buy on an auction. But what if it's free spectrum, unlicensed spectrum that you could dynamically access wherever is possible? It's a fun.
Compulsory not agree. We have been looking for using kind of these type of things, not for reducing power, but for increasing coverage in rural areas.
Very good, very good. Now, we went a little extra effort because as you start increasing your bandwidth, at some point it's becoming harder and harder to estimate your channel. So you notice that the blue curves are curling up a little bit. It's the difference between the red, which is assuming that you know the channel ideally everywhere, is in blue. I'm describing now counting the penalty of having to estimate your channel. So you see that there is a bottom where you are your sweet spot, and then if you keep increasing bandwidth beyond that, it's going to be counterproductive because of channel estimation issues. But this is RF power. Now, a very interesting question is, and a very hard question, because you cannot do it just through fundamentals and math. If you reduce your RF power, say from 100 watts to 10 watts, well, you are reducing probably the bulk of your power is going into your RF, and within RF efficiency and everything else, probably with a 100-watt transmitter in a macro network, you're burning 200, 300-watt electrical just to the RF section. Okay, so you reduce that, it's money in the bank. However, if you are now going from 100 milliwatts to 10 milliwatts to 1 milliwatt, at the expense of more and more decoding power or encoding power, now at some point you're going to be burning a lot more baseband electrical power. And this is a very interesting question, but one hard to tackle because we don't really have good models. I mean, we can go look at a particular device. There's nothing fundamental about it. 18 more months, the feature size of the silicon is going to get smaller and power is going to go down. So what are the true fundamentals of the trading of transmit power versus bandwidth when you account for the additional penalty on processing power? That's an area that needs a lot more work. Because the fundamentals you can start from today are very relevant. They tell you, for instance, that perhaps like Shannon was viewed 50 years ago, which at the time thought it would be totally relevant curiosity because it talked about infinite time horizons and infinite long codes. Well, if you wait for infinite time and you keep all your partial results, then in principle, you can go back from the results back to the original variables because you kept your intermediate variables. And so in terms of entropy, you didn't change entropy, so the physicist would tell you, you should be able to perform those operations with zero consumption of energy. Well, that's an interesting lower bound, but it's not really very helpful. And between that and looking at a particular implementation on a particular part on a catalog, it's a wide opportunity to get better models for electric consumption of processing. That's a pitch for perhaps a new area of work. So antenna elements is, of course, a very powerful one. And in the context of this Green Touch research, we've demonstrated a 16x4 array simply to show that the physics work. And if you keep adding antennas, and your target is maintain QoS, then every time you double the number of antennas, you can actually back off in the power you transmit with hopefully all the other savings. And so this is the actual experimental curve. At the bottom, as you increase the number of antennas, how you transmit power goes down. And so clearly, large antenna arrays have tremendous potential. Huge challenges as how do we deploy them economically. But there are new technologies like perhaps antennas printed in flexible plastic, metallized plastic antennas. If we could roll them out like wallpaper, there's still very big issues with how do you provide backhaul and et cetera, but you don't have to think of it as the old-fashioned big metal antenna that is very ugly and is going to make your buildings look terrible. So in summary, there's tremendous challenges ahead. But I believe also physical layer is still not quite dead. And when we talk about a factor of 2, factor of 4 capacity enhancement, and I think it could be even larger if we get to this point of extremely inexpensive, perhaps self-powered relays that are in-band backhaul that you can just stick to the walls and lampposts and get capacity boosts, which if they're that cheap, maybe 100 per sector is not out of the question. As long as you can coordinate them, you can do their resource allocation, all that magic has to happen. And there are two philosophies. Our colleague from Qualcomm did an excellent job of showing the centralized control solution. There's the other solution, which is if you have sufficient interference-driven channel access and power control, to just put the heck out of them, and they will self-power down and survive at 0 dB SINR, which with enough bandwidth, that's plenty. It's 1 bit per second per hertz. So 10 megahertz, 10 megabits per second per hertz per little unit. If you have enough of them so that most people have their personal dedicated one, that's plenty. So I think physical layer has still quite some factors to offer. It may not be the 35 that Cisco wants, but maybe it's going to delay this point in which very bad things seem to be lurking beyond the horizon, like the monster somebody showed. And so with that, I'd like to thank you for your attention.